Hello everyone. This is the first lecture style video of the semester. This video is intended to be a review for most of chapter 5 up through section 5.4. So a lot of the specifics from sections 5.1 through 5.3 aren't super important. We don't need to memorize all the names of everything. What we need to know is the general idea of what an integral is. We need to know the table of indefinite integrals from page 403 in section 5.4. And then what we need to know really well is section 5.5. Okay, so this video is intended for everything before 5.5, the general idea of integration up through 5.4. So if you don't know if you don't remember what an integral is at all, okay, that's fine. Let's just continue through this video and hopefully you'll be on good footing by the time we're done. So the intuitive way to think about an integral of a function, okay, so let's say I have my function f of x. The intuitive way to think about the integral is it's an operation that's going to give me the area beneath this curve f of x. Okay, beneath the curve and above the x-axis. So let's say I had points A and B on my x-axis. Then the integral of fx dx from A to B should give me the area in here, this green area. Okay, so it should be the area beneath my curve and above the x-axis. All right, so maybe you're asking, why do we bother finding these areas? Why do people care about areas beneath curves? Well, these areas can give us information for something a bit more abstract. So let's say my function f is actually the speed of my car, okay? The speed of my car traveling down the road. And we can see that the speed of my car is changing. It's constantly changing, right? So 1 minute I'm going 60 miles an hour, then I'm down to 55, and then up to 70. So how do I calculate how far I've traveled if my speed's constantly changing? Well, if I can integrate that function, that this area beneath the curve is that number representing my area is actually going to be the total distance I've traveled. So these integrals can give us important information about complex topics. It's not all just area, right? This area is just the intuitive idea of what it is graphically. So now the question is, how do we find areas for functions? If I'm given a function f of x or g of x, how do I find the area beneath this curve, its integral? Well, let's start first by approximating the area, right? Maybe if I have a weird curve like this, the area beneath it's really hard to calculate, right? It's a kind of weird shape. So how do I think about this area? I'm going to break it into pieces that are easier to understand. And when I'm doing standard integration, that piece I'm breaking my curve up into, it's going to be rectangles. So here I've broken up my area beneath the curve into all these rectangles, these green rectangles. And they're not a perfect fit, right? There's some error in this approximation. So for example, this area is not being counted, this area is not being counted, this area is not being counted, this area is not being counted. And then maybe right here, this area is being counted, but it shouldn't be. Okay, so this yellow stuff kind of represents error in our approximation, but it's still a pretty good approximation. So the good thing about rectangles, using rectangles for these approximations, are their areas are really easy to calculate, right? If I wanted to figure out what the area of this one rectangle is, well, that's just the height of the rectangle times the width of the rectangle, okay? So before we move on, let's consider what the area of these rectangles is. Okay, so let's consider a single rectangle here. What is the area of this rectangle? Well, its width is whatever this distance is, right? Xi plus 1 minus xi. Okay, that gives us our width. And we can denote that as this triangle xi, that's the Greek letter delta. So we call this xi plus 1 minus xi, we call that delta xi. So that's the width of my triangle. And what's the height of my triangle? Okay, it depends on how I draw, or excuse me, rectangle. What's the height of my rectangle? It depends on how I draw my rectangle, but let's say I start drawing here at this point, and then I draw my rectangle up until it hits the curve, okay? So it hits the curve here at this point. Well, what is that point? That's the function value, fxi, okay? And then I draw my rectangle straight over to the right until I get to here, and then I go back down to my x-axis, right? So our height, just to reiterate, is this distance here, which is the height of my, or the functional value of my curve, fxi. So now I have enough information to calculate the area of this rectangle, right? The area of this rectangle is going to be this, fxi times delta xi, okay? So that's the area of this one rectangle. Now, going back up to this picture, okay, so maybe that's the area of one rectangle. And to get my total approximation to the area under the curve, I should add up the areas of all these rectangles, right? Okay, so I want to add up all these rectangles. So that's what this is. Maybe this is the area of the first rectangle. This is the area of the second rectangle, area of the third rectangle, and so on. And let's say I chopped up my area into n rectangles. Okay, this is my nth rectangle. And I add all those together to get my approximation to the area. Well, this notation is a bit cumbersome, right? There's a lot of writing here. So this next line is just a shorthand for this notation. Okay, this is called sigma notation or summation notation. Okay, so this is this kind of big E, that's actually the Greek letter sigma. And what it means is we're going to add up everything that looks like this, fxi times delta xi, okay? And we're going to add up all the things that look like that, starting when I equals 1 and going up until I equals n, okay? So that's just shorthand for what we have written above here, this stuff, okay? So these two things are the exact same. They're equal. Okay. Now remember, this is just an approximation to our area right now. The question is, how can we make this approximation better? Well, maybe you've already noticed, but the skinnier I make my rectangles, the better my approximation is, okay? So these white curves are the exact same. I just copied and pasted this thing, okay? And let's look at these two cases. In the top case, I have really fat rectangles, right? So there's some error in my approximation. Again, I'll kind of highlight the error with this yellow highlighter. Okay, this is all error in my approximation, right? Okay, compare the error for this top graph for this bottom graph. Where's the error in this? Well, God, my highlighter is even too big to really color it in. I'll use a pencil. Okay, so the error is really small, right? So not much error. So I can see that the skinnier I make my rectangles, the less error I have. So if I want to get my area perfect, I need to make these rectangles as skinny as possible. Okay. And actually, to make it completely perfect, I would have to make these rectangles infinitely skinny. So what does that even mean? What does it mean to make these rectangles infinitely skinny? Well, that's going to be where we start going from just adding stuff up to actually getting an integral. That's this idea of making these rectangles infinitely skinny is where we start getting the special machinery of the integral. Okay, so let's just write down what we're saying. So we're starting with this finite approximation. We're approximating our area with rectangles. That's what this is. And then we say, okay, to make our approximation better and better, we need to take this delta xi to be smaller and smaller and smaller. We need skinnier rectangles. So the transformation comes when we start thinking about this as infinitely skinny, these rectangles as being infinitely skinny. And uh, we're not saying that they're going to be equal to 0, but think about them as skinny as imaginable, infinitely skinny. So we need to give this a new notation to distinguish between just a finite number of sums and this thing where we're adding up an infinite number of rectangles that are infinitely skinny. So we write this thing as an integral using the integral sign just to make it clear that this is something different than just this sum up here. Okay, so what does our notation become? The delta xi transforms into this dx. So think of the dx as the same thing as the delta xi. It's the width of a rectangle, but now this rectangle is just infinitely skinny. All right, and then our fxi becomes just fx. Why is that? Okay, let's go to a new page here for a second. So let's say my curve looks like this. When I'm doing the rectangles, okay, what are my fxi's? They're where my rectangle first hits my curve, right? So in the beginning, I have maybe just n values of fxi. So maybe fxi is here, 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 right? And as these rectangles get skinnier and skinnier and skinnier, I have more of those values, right? So when the rectangles are just super skinny, now my fxi's are here, 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 and let's say I continued on and they would be here, 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 here. Well, as my rectangles get infinitely skinny, I have infinitely many of these fxi's, so eventually they're just everywhere. So now instead of considering rectangles, going back to our original page, now instead of considering rectangles with just an infinite number of rectangles with these heights fxi, now I'm considering an infinite number of rectangles, and every point on my curve is actually going to be the top of a rectangle. So like every fx is going to be the height of some rectangle. Okay, so that's why I go from fxi to fx. And then the transformation from this sigma notation into our integral sign, that's just to denote that, okay, we have these infinitely skinny integral or rectangles. So we just give it this special notation. And then the bounds a to b tell us where we're integrating. We're integrating from a to b. So this is the transformation from our rectangles to our integral. And remember that the rectangles, this summation is an approximation, and this integral should give me a true value. Okay, so far we've seen that our approximation by rectangles becomes our integral. This is just what the integral is. Now let's start talking about how we calculate the integral. Okay, so far we've done what, now let's do how. The key concept that's going to allow us to calculate integrals is the connection between derivatives and the integration. And in particular, we need something called an antiderivative. Okay, so to explore this connection, let's think of a function capital F of x, and let's say this function is differentiable. Let's say it exists on this interval a b, and I know what capital F of a is. let's also assume I know what f prime of x is for all x in that interval a, b. Is this enough information to figure out what fb is? So remember the graphical idea of what a derivative is. If I have a function like this, let's just think of this by itself on its own little plane. At this point x, what is f prime of x? F prime of x, let's see, there's a line tangent to our curve, right? That goes like that. And f prime of x is going to be the slope of that tangent line. Okay, so that graphical idea of what a derivative is very important. Okay, so if I know what, well, let's look at our function here. Let's say I know f prime of a is right here, or excuse me, f of a is right here. And I know the derivatives everywhere on this interval. Is that enough information to figure out where fb is? Can I kind of reconstruct my graph from this information? Well, let's start by doing an approximation. Okay, so I know what fa is, and I know the derivative at fa. Let's say my derivative has, a certain slope, so the tangent line at that point should look something like this. Okay, and if the interval is small enough, my function should behave very similarly to my tangent line. So this green line is an approximation to what my function looks like on this small interval. And let's say, okay, so we're saying that my function should be approximately at this white point. Okay, at this point, we'll call it x2. All right. Now what? Now I know what the tangent line at this point looks like as well. I know the derivative here. Maybe my tangent line looks more like this now. Okay, and so my function should be approximately here. And then I know my tangent does this. And then my tangent does this. So I end up with this approximation to my curve. And I'm saying this is about FB, approximately FB. Okay. Can I make this approximation better? Yeah, by adding more points in here and making the distance between them smaller. Okay. Okay, so now let's do another approximation. Maybe I have another approximation, this yellow line, but this time I have more points. So I get a bit more detail in my curve. And maybe when I do that, I get a bit better approximation where my point FB is there. If I add more and more points, I get a better and better approximation. Let's say eventually I add just a ton of points and I see that my curve looks something like this red line here. Okay, so a nice smooth curve. How can I write down the approximations to my curve? Well, what I've done here is I've said, okay, FB is approximately f of a plus the little tangent line between a and the next point, okay, plus another little tangent line connecting to the next point, and then the next point, and so on, okay? So how can I write this in a nice compact, this is a lot of writing, how can I write this in a nice compact notation? I'll have FB is approximately FA. I'll leave that FA by itself. And then let's use that sigma notation we used previously to write all this similar stuff as one short compact expression. That would be f prime of xi times delta xi from 1 to n. Now, does this notation remind you of anything? It looks a lot like the approximation to our integral, right? When we were adding up all those rectangles. So as I add more and more points xi, and the distance between the xi's goes to 0, meaning this delta xi goes to 0, what does that become? It should become the integral. So I should have fb is equal exactly to fa plus the integral from a to b of f prime of x dx. Okay, and just rearranging, I'll get fb minus fa is going to be equal to the integral from a to b f prime of x dx. And here we see the connection between integrals and derivatives. So let's say I'm integrating some function f prime of x. And I know that f prime of x is the derivative of this f of x over here. In other words, this capital F of x is the antiderivative of f prime of x. Well, then I know the integral of f prime of x is just going to be fb minus fa, where a and b are my bounds here. Okay, so when I have let's go to a new page for a second. Let's say I have a function g of x dx, and I'm integrating from a to b, and I know g is derivative of some other function. Let's call it capital G. All right. In other words, g of x is antiderivative of little g of x. Then the integral a to b g of x dx is going to be this antiderivative at b minus antiderivative at a. So this is that strong connection between derivatives, antiderivatives, and integrals. Okay. And this is restating what I've said on this separate page. Let's say I want to find the area beneath the curve gx between a and b. And I know gx, little g of x, has this antiderivative, big G. Well, then the integral of little g from a to b is just going to be big G at b minus big G at a. Okay, so again, we call this big G of x the antiderivative of little g. What does this mean? It just means that if I take the derivative of big G, I'm going to end up with little g. Just a quick note that the antiderivative is also known as the indefinite integral. Okay, so they're synonymous. And how do we denote this? We would denote the antiderivative or indefinite integral as an integral sign with no bounds. Okay, so when I see this here, the integral sign of x cubed dx, what this is really asking is it's asking you to find the antiderivative, just the antiderivative. So our answer is going to be a function, not a number. Okay, so now instead of looking for an area, we're just looking for the function, the antiderivative of x cubed dx. So we're looking for the function whose derivative is going to be x cubed. So how can I find that? It's very similar. It's basically just the opposite of taking the derivative. Okay, so I ask myself, what function has a derivative of x cubed? How can I find that? Let's go to a separate page real quick. Let's say I had xn and I wanted to find the derivative of that. Okay, what would I do? I would multiply by n and then subtract 1 from the power, right? All right, so what if I want to do the opposite of that? What if I have xn and I want to find this antiderivative? What am I going to do? Well, instead of let's start with the exponent. Instead of subtracting 1, I'm going to add 1. Okay, and then instead of multiplying by n, I'm going to divide by this n plus 1. Okay, so my antiderivative of xn dx is going to be x to the power n plus 1 over n plus 1. Okay, we're not quite done yet, but let's go back to our document now. So let's apply this rule to our x cubed. Okay, so what am I going to do? I'm going to add 1 here. I'm going to add 1 to 3. 3 plus 1 is going to be 4. Then I'm going to divide by that same 3 plus 1. And I end up with x to the 4th over 4. Okay, so that's my antiderivative. And can I double check that? Well, yeah, if I take the derivative of this thing, I should end back up at x cubed. So let's just double check real quick. Let's see if the derivative is equal to x cubed. Okay, so I take the derivative of x to the 4th over 4. I bring the 4 down and subtract 1 from the power. Those 4s are going to cancel, and I'm going to end up with exactly x cubed. Great. So the antiderivative of x cubed, also known as the indefinite integral of x cubed, is just going to be x to the 4th over 4. Okay. But there's something interesting going on. What about x to the 4th over 4 plus 1? If I take the derivative of that, well, the derivative of 1 is 0, so that 1 gets totally canceled out. And so the derivative of that is x cubed as well. And same thing with x to the 4th over 4 plus 2, and x to the 4th over 4 plus 3.0019. And really, any constant I can think of. If I add a constant on the end, it's not going to affect the derivative at all, right? So really, there's an infinite number of functions that have the derivative of x cubed. So we say there's a whole family of antiderivatives for x cubed. So how can I represent the fact that there's a whole family of antiderivatives? Well, I'm going to say that the derivative of x cubed dx, or excuse me, the antiderivative of x cubed, okay, so the indefinite integral x cubed dx is going to be equal to x to the 4th over 4 plus c, where this c, we call it the constant of integration, and it represents the fact that we can add any constant on to the end of our antiderivative, and it's still going to be an antiderivative. Okay. So this is really where the rules of integration are going to be applied. It's in finding these indefinite integrals, these antiderivatives. And there's a whole table of this stuff on page 403 of the textbook. You should all have access to an electronic copy of the textbook on WebAssign. So that's going to be on page 403 in section 5.4. Okay, so there's a whole list of rules for antiderivatives, and most of them should be familiar in that they're the opposite of the derivative rules for the most part. Okay, so now let's take this tool of finding the antiderivative and let's go back to our definite integral, right? So our definite integral, we're looking for that area beneath a curve. We're looking for a number to be our answer. And this indefinite integral is just a tool that we use to get there. Okay, so once we get our antiderivative, okay, our function g of x, that's our antiderivative of little g, we're just going to plug our bounds in to that function big G. and then we're going to do big G of b minus big G of a is going to be equal to my integral g of x dx. So let's see an example real quick, a concrete example. Let's find the area beneath the curve of fx equals x squared plus 4 between the points -4 and 3. Okay, so in the simplest language possible, we just need to evaluate the integral from -4 to 3 of x squared minus 4. Okay, so I've rewritten my integral here, -4 to 3 x squared minus 4 dx. The first thing we need to do is find that antiderivative of x squared minus 4. And let's go to a new page real quick. I want to find the antiderivative of x squared minus 4. So the indefinite integral of this. Okay, I just use my power rule for this stuff. Well, let's see, if I have x squared, the antiderivative of that should be x cubed over 3. And then if I have a constant, the antiderivative of that, I'm just going to multiply by x. And then there would be a plus c, right? So there should, if all I needed was a indefinite integral, I would have a plus c on the end. But now let's see what happens when I plug in. Okay, let's say instead of doing a indefinite integral, I was doing a definite integral. Let's say I had bounds. Okay, my next step would be evaluating this thing from x cubed plus c. So this bracket with b and a on the right side, that just means, okay, this is my antiderivative, and my next step is to plug these bounds in to my antiderivative. Okay. So let's leave the plus c there for a second and see what happens. Okay, if I let's plug b in first. Okay, if I plug b in, I'm going to get this thing, b cubed over 3 minus 4b plus c. And then I'm going to subtract what I get when I plug in a. Okay, so I get minus a cubed over 3 minus 4 times a plus c. Now, forget about everything else. Look at the c's, right? I got a plus c here, and then I got a minus plus c. So if I distribute everything, I'm going to end up with c minus c. And then I got blah, blah, blah over here. So it doesn't really matter what I'm trying to, this is going to be important for the integral, but what I'm trying to show is that these plus c's, when I do a definite integral, these plus c's are always going to cancel. Okay, so all I'm going to be left with is this stuff. Okay, so what am I trying to say? I'm saying when I have a definite integral, I don't even need to bother writing the plus c. Okay, so I find the antiderivative, and then I don't need to write the plus c here. Okay, I can just do my bracket BA. Okay, and then the next step would be plugging these in. So I'll say that we don't need the plus c for definite integrals, but if I just had this, okay, so these are two different cases. If I had the indefinite integral, I definitely need the c. So this is kind of a definite versus indefinite, the difference between these two things. Okay, let's in the definite case, we're looking for a number that represents our area beneath a curve, right? So we find the antiderivative, that's just a tool that we use to find our area. Then we plug our stuff into our antiderivative and we get a number at the end. This 7 over, I think the answer is 7 over 3. In the indefinite integral, when we don't have bounds, let's see, so in this case, we were using the bounds, I think, -4 to 3. When we don't have bounds in this indefinite case, we're no longer looking for an area, we're just looking for this antiderivative. So we find this antiderivative, we write a plus c on the end representing the fact that, well, there's a whole infinite family of answers, and then this is where we stop. Okay. So back to our example, I'm looking for the area beneath the curve from -4 to 3 of x squared minus 4. I find my antiderivative, and I don't need to write the c. Then I have my bounds here on the right side from 3 to -4, or -4 to 3. The next step is to plug my bounds in to my antiderivative, okay? So I plug in +3 here to my antiderivative. So I have, instead of having x cubed over 3 minus 4x, I have 3 cubed over 3 minus 4 times 3. Then I subtract what I get when I plug in a. So this is what I get when I plug in a, and I subtract this from this. And the rest is just simplifying, okay? It's maybe not always easy, but it's pretty straightforward. So I'll leave it as 27 over 3 for now, minus 12, minus -64 over 3, minus -16. So maybe an area where we have common mistakes is not distributing the negatives correctly, okay? So if I distribute all the negatives correctly, I should end up with 27 over 3 minus 12 plus 64 over 3 minus 16. Simplifying that all, I get 7 over 3. Okay. Now, let's just talk about the idea of integrals representing area. We said an area integral represented the area when f was greater than or equal to 0, so when this function was always positive. What about when the function's not always positive? What if our function's positive for a little while, then goes negative? What would that shaded region look like? Well, it would be this green shaded region, okay? The integral now, let's see, if I just integrated from a, let's call this point d. If I integrated from a to d, I would get this area, and that would be a positive number, okay? And then if I integrated from d to b, I would get this, and that would be a negative number, okay? So does negative area make sense? Well, not in the usual way we think about it, but let's start thinking of it as these integrals as representing signed area, okay? So maybe I integrate this whole thing from a to b. I do it all in one step, and it's possible for my area, my integral to be equal to exactly 0, meaning, okay, the area beneath the curve is 0. Well, how does that work? Because there's obviously some area here and area here and area here, but this area is positive, this area is negative, so they cancel out. So while area beneath a curve is a good way to start thinking about an integral, we need to expand our thoughts to incorporate these negatives and start thinking about it as signed area. So I can integrate a function, and maybe I have a little positive area here and negative area here, and maybe they completely cancel out, or maybe one's slightly bigger than the other. So I could end up with positive numbers, negative numbers, I could end up with 0. So it's not quite as simple as just being area. Okay. So real quick of why we would use signed area. Okay. Let's kind of go back to our car example, right? So I have a car that's traveling, let's say it's traveling east. And the curve represents the speed I'm traveling east, okay? So let's say when my curve is up here, okay, this is my speed. Let's say this is my speed axis. And this is my time axis. So at time, let's say at time A, I'm traveling at this speed, S1, okay? and I'm traveling east at speed s1. Okay, so my speed's constantly changing, and then maybe eventually it hits 0 and then becomes negative. Okay, well, what does it mean for my function to be negative now? Well, if positive was my speed traveling east, then negative should be, well, what would the opposite of east be? This would be my speed traveling west, right? Okay, so then what would my integral be? What would my integral give me? Well, from my previous example, okay, maybe I know that this shaded region here, the integral of this piece, that's going to be my distance traveled east, right? And then this integral here, that's going to be a negative number. That negative number would be the distance I've traveled west. So I get a positive number here, I get a negative number here, and I add them out, and I'm actually going to get the total distance I've traveled. If it's a positive number, I've traveled a distance east in total, and if it's a negative number, I've traveled west in total. Okay, so maybe the value of this region is like, maybe this is 100, and then this value is negative 25. Okay, so that I would add those two together and I'd get 75, meaning, okay, I've traveled positive 75, meaning I've traveled positive 75 in the eastern direction. If, on the other hand, I had a function that looked like this, okay, so it's positive for a little while, and then it's a lot more negative, right? Okay, so maybe this value is 30, and this is 100, negative 120, okay? So in total, I've traveled negative 90 miles east, which is what? That's just 90 miles west, right? So this is how this idea of signed area can be useful. So let's just kind of review now the definite integral versus the indefinite integral. All right, the definite integral is going to look like this: a to b fx dx. The fx will be, we're going to be given a specific function, we're going to be given specific bounds. So the a and b should be numbers, and the stuff inside the integral should be a function. So an example would be the integral from pi over 2 to 3 pi of sine of x dx. Okay, what is the result of this integral going to be? It's going to be a number, and that number is going to be the signed area. So maybe it's going to be a positive area, a negative area, maybe it's going to be 0. We call that a signed area. And to find this number, what do we need to do? We need to find the antiderivative of our function and then plug our bounds into our antiderivative. What is an indefinite integral? It's the same setup, but we don't have any bounds, right? We just have an integral sign in our function. Okay, so in general, we're going to have integral sign f of x dx, no bounds. So what are we looking for here? Now we're not looking for a number, we're not looking for an area, we're just looking for that antiderivative, that function or family of functions whose derivative is going to be equal to that function inside the integral. So that's the only thing we're looking for when we have an indefinite integral. Okay, so we're just going to end up with a function, and then we have that constant of integration plus c. All right, that's about it for the lecture portion of this video. I'll do a problem video where I show the mechanics of solving these problems. So this is the theory, and then I'll do another video with more of the mechanics. All right, that is all.